Okay, so now we're going to look at the second method for getting the distribution of new random variables. So last time we looked at the CDF method, where you get the CDF and then you differentiate it. And this time we're going to look at the transform method. So first of all, let's just recap some definitions. So we're going to define a increasing function if I have 2 points, y1, which is definitely less than y2, then the function of y1 is less than the function of y2. So, the main idea at this point is you have a function that does this, and it's always going upwards. It never does that. And we can also have the decreasing version where it's always going down. It doesn't have a plateau, so no plateau, it goes down. So let's assume we have a PDF y, and then we have a function of that that is either strictly increasing or decreasing for all y. Then if I want to get my new PDF, I just substitute in. Now by h minus 1 here, I'm referring to the inverse function. And I'll show you some examples of how to do that. And obviously these lines here are for the absolute value of this. And you just substitute in and that's it. So all you would need to do is find the function, find the inverse, and then substitute in. So here's the method. We're going to have a new random variable u that's going to be a function h of y. And we've got the idea that it's strictly increasing or decreasing function. So what you do is you quickly find the inverse, you then differentiate it, and then you substitute into this formula. The other thing you can do is imagine that you don't have a function that's always strictly increasing or strictly decreasing, but you could break it down into regions, and on that region it's strictly increasing or decreasing. Well, what you do now is you basically end up with a inverse function for each region, and then you just add together each of these things. So basically you're doing the same method before, you're doing one for each region, and then you just add them all together. So let's do an example. We've got y has a PDF where its support is between 0 and 1, and between these two it's 2y and it's 0 elsewhere. And I've got a new function u which is 4y plus 3. And we want to work out the PDF. So first of all, let's quickly draw a picture. So if this is y, and we've got 0 and we've got 1, we find that this is our u. So this is our u equals 4y plus 3. And this will go from, well, when y equals 0, we get 3. And when y equals 1, we get 7. So there's your function, and you can see that is strictly increasing. So given that, what we should do next is we should do some calculations. So we've got that u equals 4y plus 3. So I'm going to rearrange that to get y in terms of u. So if you look at that, you can see that y equals u minus 3 over 4. And this is our inverse. We've basically, our function h goes from y to u, and now our inverse will basically go from u to y. So we denote that as h minus 1 of u equals u minus 3 over 4. So now I need to differentiate that. So I need to do dh minus 1 u over du, which is just going to be a quarter. And then I'm going to take the absolute value of that. So an absolute value of a quarter is just a quarter. So now what do I do? Well, to get my function, my f of u, first of all, I'm going to write my 2y. And wherever the y is, I'm going to substitute in what y equals. Well, so we've got this here, we're going to substitute in. So this is going to be what that is, which is u minus 3 over 4. I'm going to times that by the absolute value, so that's this number here, a quarter. And when I simplify that, I should get u minus 3 over 8. Now we just have to work out what the support is. So we know that the support of y is between 0 and 1. So we know that the support of u is between 0 and 7. So putting it all together, we got f of u equals u minus 3 over 8 for 3 less than u less than 7 and 0 else. All done. Well, let's look at something a bit more complicated. We've got y is a standard normal and u equals y squared. What is the PDF? So let's actually look at our diagram first of all. So now here is our y, here is our u. We get something that looks like this. And we're going to have to split that into two regions, because on this region here we have strictly decreasing, while this region here is strictly increasing. So I'm going to split this into two regions, do the process for each region, and then add those two together. So let's just go back for a second. I'm going to call this region 1 and region 2. So let's have a look at region 1, which is the case where y is less than 0. So we've got y equals u squared, and the inverse is going to be y equals u, the square root of u, but minus, because we want to be able to get that negative side of that. That means that our h1 minus 1 of u equals minus the square root of u. Now we will differentiate that, so h1 minus 1 of u du, and that is going to be minus 1 over 2 the square root of u. And we're going to take the absolute value of that, which is going to be 1 over 2 the square root of u. So good, so that's region 1. Let's now do region 2, which is where y is greater than 0. It's very similar. We've got u equals y squared. So y equals the square root of u. This time we're on the positive side of it. So now h of 2 minus 1, because this is our second inverse function of u, equals square root of u. And if I differentiate that, that's going to be 1 over 2 square root of u, and then I take the absolute value, which is 1 over 2 the square root of u. Right, so let's just remind ourselves, f of y for standard normal is 1 over 2 pi, the square root, e to the minus y squared on 2. So now f of u, well, we've got to have two bits that we're going to add together. We've got the region 1, so we've got 1 over 2 pi, square root, e to the minus, well, we need to substitute in for y. Y on this side is minus the square root of u squared on 2, times by our absolute value of our first derivative, which is 2 the square root of u, plus, we've got exactly the same thing now, e minus, but this time it's the square root of u squared over 2, 1 over 2 square root of u. Well, if we take the minus square root of u and square it, we get u. If we take the square root of u, square it, we get u. So in fact, we've got the same thing twice. So if we simplify that, we have e to the minus u over 2. We've got the square root of 2 pi. We've got the square root of u. Obviously we've got a half and a half, so that settles out. And we can rewrite that as e to the minus u over 2, u to the minus a half over, I'm going to call it root 2 and root pi. I just split it. Why? Because if you actually look at that now, what we've got is you've got a chi-squared with 1 degree of freedom. And as we also saw last time, that is a gamma, where alpha equals a half and lambda equals a half. And I'm using the fact that gamma of a half equals root pi. So there we are. We showed using the transform method that we actually have, if we take a standard normal and we square it and we look at that distribution, we have a chi-squared with 1 degree of freedom. Okay, that's the end of week 6. Next week, after the mid-semester break, we are going to start looking at the method of moment generating functions, which is the third method of doing transforms. Okay, if I don't chat to you, have a really good mid-semester break, and I'll see you afterwards.